So one of the challenges I set for myself in this coronavirus quarantine is to figure out what this formula means. I'm not a mathematician. I took some math classes 30 years ago in high school and college, and so I have not been involved with it that much. But this is a formula that always kind of interested me, and I figure, heck, got some time on my hands. So for the last month, I've put in a couple hours a day trying to figure out what this means. What are these symbols, and how does it all fit together? So here's a little, hopefully 10-minute tutorial on what this means. Now there's a short version that lasts about 30 seconds, and if you just want to listen to that, you can turn off the video and go on your merry way after that. So here's the short version of what this means. Imagine there's a dog, here's a fence, and the dog chases after people walking by over here. Chases after them. So the owner decides, hey, I'm going to put this dog on a leash, a 1 meter long leash. Well, the next time the dog starts to chase after someone, the leash is going to go taut right here. And with that next leap that the dog makes, he's actually going to head up this way. And if he leaps hard enough, he's going to leap all the way, and the collar is going to be taut all the way around, and he's going to land over here 1 meter over on this side of the fence, upside down, wondering how he got there. That's what this formula means. Here's another example. Let's say you're standing on top of the earth, and you take a step in this direction. You take one step. Everybody around you in your room, your living room, they see that you just took one step. Okay, everybody agrees. Yeah, you just took one step. Now, let's say you stand there and wait 12 hours as the earth rotates, and now evaluate where you are in your living room. Well, everybody still sitting there 12 hours later will still agree, yeah, you took a step, and nothing changed. You just stood there for 12 hours. But to an outside observer looking at the earth, an outside observer would say, you didn't step that way, now you're actually stepping that way. A +1 in that direction is actually a -1 in that direction. That's what this formula says. That's the short version, and you can turn off the video now if you like. I'm going to give you a little bit longer version that makes sense to me, and makes sense to hopefully a newcomer to the subject. Here are a lot of different things I've studied over the last couple weeks. They're all fascinating, and they all relate to this formula. However, I don't think I need all of them to describe it. Here's what I do need. I do need to talk about E. I do need to talk about pi. I do need to talk about I. I do need to talk about exponents. But these other things, sine and cosine, fascinating. How sine and cosine correlate with each other is a very interesting subject, but I'm not going to get into that. Infinite series, I don't understand that very much, but that's one way that people describe this. Complex numbers, polar coordinates, all fascinating subjects, but I don't think we need all that. Here's what we do need. Here's this original formula, Euler's identity. E to the pi I plus 1 equals 0. Well, right off the bat, we can simplify it. If we subtract 1 from this side, subtract 1 from this side, here's the formula you end up with. E to the pi I equals -1. And that's interesting because both those sides are equal. In other words, this is this. They're just another way to say each other. If I say I'm $1 in debt, I could also say I'm e to the pi I in debt. I owe you e to the pi I dollars. I owe you $1. So it's another way to look at it. So over the next couple minutes, I'll break down what does e mean, what does the exponent form mean. You have a number to an exponent or two. What does the pi symbol mean? And what does the I symbol mean? And how does that all fit together? Okay, starting with E. The simplest explanation is when they first discovered the number e, here's how they did it. They said, okay, let's talk about interest. If you have $1 and at the end of the year, your banker pays you 100% interest at the end of 1 year, how much money will you have? Well, here's how you figure it out. You have $1, and at the end of the year in December, the banker pays you your dollar back plus 100% interest, and it happens one time at the end of the year, you'll have $2. All right, what happens if you do two different payments? Well, you have $1, and then halfway through the year, your banker pays you 50% of that. So you have $1 and you get 50% of that. Great, that's $1.50. And then at the end of the year, you take the other 50% of $1.50, which is 75 cents, add them together, now you have $2.25. Okay, what if you have 4 different payments? March, June, September, December. Well, at the end of that year, you'll have $2.44. What if you add the interest in each day of 365 days of the year? Daily interest, you'll have $2.71. If you do it each hour, each minute, or each second, you do it millions of times throughout the year, you'll also have, wait a minute, $2.71, the same. And that's the magic here, is if you take more and more interest intervals and do the tighter and tighter intervals, each second you give a continuous interest all the time throughout the year, always adding up to 100%, but continuous interest, you will reach $2.71, no more and no less ever. That's what you'll get with continuous interest. That number is E. So $2.71 or 2.71 is E. And that number is what you get when you continuously grow something. You continuously push it every minute, every second. That's how much you'll get starting with, if you start with the quantity of 1, you'll end up with $2.71. And here's kind of a look at the formula. $1 times E to the 100% rate in 1 year. That's what it kind of looks like. And here's the formula that they actually use. The principal that you start with, and then you multiply E, or bring E to the RT power, the rate times the time. One interesting thing about this is rate times time. That reminds me of driving a car. Speed times time. 60 miles an hour times 1 hour will get you a distance of 60 miles. So RT can be thought of as a distance. You have a principal and you push it continuously for a certain distance. That's the quantity that you'll get at the end of the year. Here's another way to look at this shape formula. P to the ERT looks kind of like this, doesn't it? 1 to the E pi I. Well, that was kind of what we were originally looking at, right? With a 1 out in front of it. So notice the similarity there. We'll come back to that later. The next thing to talk about is exponents. What does an exponent mean? When we look at this original formula, E is being raised to an exponent up here. All right, so what does that mean? An exponent, with an exponent, you can form any positive number. If you just choose a number and raise it to a variety of different exponents, you can form any number. So for example, if I pick the number 2, and I raise it to the 6th power, that means multiply 2 times 2 times 2 times 2, 6 times, and that will be a 64. And look at the difference. If I would have just added 2 together, 2 plus 2 plus 2 plus 2 plus 2, I would have just got 12. So exponential growth is much faster than just normal additive growth. So that's what exponent does. It multiplies a number that you choose by itself many times over and over again. Here's the graph of what an exponential curve looks like. And here's the line of what an additive line looks like, 2 plus 2 plus 2 plus 2. If we add 2 plus 2 together one time, we get 2. 2 times 4. 3 times 6. 4, 5. We add 2 plus 2 6 times, we get a total of 12. 12. Now, if we start factoring in exponential growth, if we do 2 to the 6th power, 2 to the 6th power, we get 64. So that's a huge growth with exponential power. Exponents make a number start out small, and then as you move this way, it grows really rapidly. So as you travel a distance in this direction, as you move this way, on the number of times that you're multiplying something together, you get a rapid growth. Now, you can choose any number as this base number. And in fact, why don't we go back a page and talk about e and just plug e in for that number, 2.71. So if we use a graph of 2.71 to the first power, to the second power, to the third power, to the fourth power, on like that, we also get a curve like this. It's a little bit steeper than this one, but this is 2.71 to the first power is 2.71. 2.71 to the second power is 7.38, to the third power, etc. Now here's an interesting one. What if we do e to the pi power? E to the pi power is 3.14. That's about 23. So interesting little side note there. Anyways, e to the fourth power goes way up here, and it's 54.6. So it increases rapidly. Point to remember here is the distance traveled into the exponents as you move right on this exponential graph here. The distance traveled into the exponents determines how large the result is. That's all there is to know there. All right, moving on to what does pi mean? Let's say that you have a circle and you have a diameter going across the circle here. If you stretch a string across that diameter and then grab that string and run it along the outside of the circle once, and then move it over twice, and then move it over 3 times, you'll still have a little bit extra left over. So it'll go around 3.14 times. That's how they came up with the number 3.14, and then they call that number pi. Let's say you don't have a whole circle. Instead, now you just have half of a circle. Okay, forget about this lower half. Well, for half of a circle, instead of taking the whole diameter, if you just take the radius, just this half right here, this radius, and stretch this radius around the outside of this circle once, twice, 3 times, and a little bit more, the radius, and that distance right there is called a radian. It will be 3.14 radians. So pi radians are in a half circle. Starting here, if pi radians are a half circle, this part of the circle would be half pi, 1/2 pi. This would be pi, this would be 3/2 pi, and going all the way around the circle would be 2 pi. The important thing to remember here is 3.14 radians is the same thing as half a circle. Half a circle is the same thing as pi. All right, moving on to what I is. Here's an example. Let's say you have a person standing on this dot here, and this person takes a step, 1 step in this direction. All right, so the person took 1 step. Now, let's say that the person actually, we take this person and rotate him around 180 degrees, or pi radians around, so he's facing that way, and notice, oh, now this foot is over on this -1. All right, so the distance that this person took is still 1 step, it's just in this direction. So the person has still taken 1 step, it's just now there's something else going on there. So you may know that you can always multiply a quantity by 1. 1 times something is just itself. Well, the square root of 1 is also 1. So in other words, you can always multiply something by the square root of 1 without changing it. So just for the fun of it, let's multiply 1 step by the square root of 1. It doesn't change a thing. On this one, let's multiply 1 step by the square root of 1. It doesn't change a thing, but then we put a negative mark in front of it to indicate that we're now on this side, not on this side. Okay, so 1 step in the positive direction, 1 step in the negative direction. Now, let's say, so we rotated pi radians. We rotated that man all the way around there for that. Let's say that we rotate this little man, we rotate him just up just 90 degrees. So his foot is now pointing straight up in the air. Well, we can't graph it on this number line here. His foot's sticking straight up in the air. Now, he still took 1 step. I mean, his foot is still 1 step apart. It's just coming up out of the page, and we can't represent it on a flat piece of paper like this. So here we have to say, yeah, the little man here took 1 step, but we need to make some indication here that we can't graph it on here. It just doesn't work. It's in a zone of the world, zone of the universe. It's in a region that we can't diagram. And the way mathematicians do that is instead of multiplying by the square root of 1, they say, okay, let's multiply by square root of negative 1, which is kind of a meaningless number because there is no square root of negative 1. You can't multiply something times something else and get negative 1. It just doesn't work. But using a 1 here means that you don't change the length of the step. Like if you stuck a 2 or a 3 in here, multiplied it by that, it would be a 2 foot wide step or a 3 foot wide step. So we have to use something from the family of 1s here, but make it kind of meaningless. So that's what they do is they do square root of negative 1, which means it's still a length, it's still a 1 step distance, but we can't, it's in a plane, it's in a part of the paper that we can't diagram. Square root of 1 is the number I. That's what they use I to represent the square root of negative 1. Now, let's say we rotate the man down so that the foot is pointing down into the table. Now, from our perspective, we couldn't see the length of the step, but we know since we rotated it, we know it's 1, the length of the step is 1, it's just pointed down. So we represent that, he took 1 step, it's pointed either up or down, we can't tell which, but we can't see which way it's going. Oh, it's pointing down, okay? So this man here is taking 1 step. If we rotate him 180 degrees, or pi radians, it'll be a negative 1 step. If we bring it back and only rotate it 1/2 of pi, it'll be called I step. And if we rotate it 3/2 around, it'll be a negative I length of a step in the negative I direction. So I indicates a direction of motion that we can't perceive. It's coming straight out of the page or going straight down into the page. I is a reminder that the magnitude we're working with, which is 1 length of a step, the magnitude we're working with points in a direction that has no effect on our perception of the real world nearby. So it's that the foot is sticking out of the page or down into the table. We can't really diagram that here. It doesn't really fit on this graph that we're working with. So we use I to remind us that magnitude is pointing one way or another that we can't really measure. So that's all you need to know. We'll come back to the very first page now, and now put it all together. So what this equation is telling us is that if we take a quantity of 1 is invisible in front of here. You can multiply 1 by anything. If we take a quantity of 1 and we push it continuously, for a distance of half a circle into the I dimension, we'll be at negative 1. And if we're at negative 1 and we add 1, we'll be at 0.